Good afternoon, everybody, and welcome to MOS Live for our virtual planetarium exploring space. My name is Karen. I'm one of the many educators at the museum, but today I'm going to be acting as your moderator. This just means I'll be sort of hidden in the background, keeping an eye out for all of your questions, your comments, your observations, and I will share them with our planetarium educators. Now, here on Zoom, if you do have a question or observation, you can click on the Q&A box and just type that right in and send it off to me. If you are on Facebook or YouTube Live, we so appreciate that you are tuning in today, but unfortunately, we cannot see comments or questions from there. Now, lastly, if you do need captions today, you can click the CC button here on Zoom and choose Show Subtitles. So with that, I want to invite our Planetarium crew to come on and introduce themselves.
Hello, everyone. My name is Katie. My pronouns are she and her, and today I will be your guide as we talk about gravity, but I can't do it alone.
Hello, everybody. My name is Talia. I use she, her pronouns, and I am going to be flying you through space and otherwise providing visual support.
Yes, that'll be awesome. Thank you, Talia. So as I mentioned, today we are going to be talking all about gravity. The month of March is our space math month, where we're taking mathematical concepts and bringing them to you in the form of things that happen in space. And a lot of the concepts, especially this one, is gravity, something that we're all really familiar with, but it's actually at its core kind of really difficult to understand, and it is not completely understood even now. So I'm going to try to tackle this concept and bring you definitions and theories of gravity from a couple of different places, and then we'll talk about how things orbit and why they orbit and just how it all works. And please feel free throughout the program today to type in any questions you might have. I'll try to pause throughout the program so that I can take questions, or if you have comments, observations, that kind of thing. All right, so to start us off, we're looking at the Earth right now, because I thought starting close to home and starting with things that we're more familiar with is probably a good spot. So gravity itself, what actually is gravity? Well, gravity is kind of a phenomenon that where anything that has mass or anything that's made up of stuff has gravity, and gravity causes objects to move together, so to be attracted to each other or gravitate toward each other, right? It's not really like an attraction like positive and negative charge. It's not that type of a interaction there, but it's more just the bigger something is, the more other stuff is going to move toward it. So when I say anything that has mass has gravity, I literally mean anything that has mass has gravity, including the Earth. Anything that you can touch or feel, your own body, the air around you, if it has mass, it's got gravity. It's just that the Earth's gravity is so much stronger than the gravity of you or me or anything that's actually on the Earth. So an apple, for example, that's got gravity. And anything that has gravity is actually pulling on everything else. So the Earth has a ton of gravity. That's why we are stuck on the surface of the Earth. But as the Earth is pulling on us, we are also pulling on the Earth just a teeny tiny bit. Now, since we're so much smaller compared to the Earth, our gravitational pull is so little that it's basically non-existent. We can't actually really measure it at all because the Earth is so much more massive than we are. But we can also look at an example using the moon. So the moon is less massive than the Earth, and the moon is in orbit around the Earth, so it's affected by Earth's gravity. But the moon also has its own gravitational pull on the Earth, and we can see evidence of that in the tides, for example. So even though the Earth is a lot more massive than the moon is still pretty, it's holding its own a bit. So it also pulls on the Earth, and we can see those physical effects in the tides. Now, the sun has the most mass of anything in the solar system. And so it has the most gravity as well. And that's why all of the planets are in orbit around the sun. And the sun is also pulling a little bit on the, also has an effect on the Earth's tides as well. So all of the planets, so Talia is showing us a nice solar system overview here. You can see all of them orbiting around the sun. And that's because all of the planets are so much less massive than the sun is. The sun composes 99%, over 99% of all mass in the solar system. But the planets also have an effect on the sun. So we can't really see it, but the planets are also pulling on the sun, causing it to wobble just a little bit. And it turns out that this method is actually really useful for finding planets in other solar systems, but we'll talk about that a little bit later. So let's back up a bit and talk about who came up with the first theory of gravity, or maybe who used this term in this way before, and that would be Isaac Newton back in the early 1600s. He was a physicist among many other professions, but he was the first person that kind of made this connection of mass and this pull or this attraction, right? There's the old story that's probably not entirely true, but of him throwing an apple up in the air or him getting hit in the head with an apple, and that kind of sparked this idea of gravity. And so he theorized that anything that has mass in the universe has gravity, and anything that has mass and gravity is affecting everything else. So one object in one part of the universe that has mass, also has gravity, is affecting another object that has mass millions or billions of light years away in another part of the universe. So what essentially he's saying is that the effects of gravity are infinite. They just get less depending on distance. So the farther away two objects are, the less force of gravitational attraction is going on between them. So even though, you know, Pluto is really, really far away from the Earth, technically there is still a teeny tiny amount of gravitational interaction happening between Pluto and the Earth. So his kind of main analogy for gravity was almost like a string. So if you imagine the sun is at the center of the solar system here, and imagine there are strings going out to each planet, and the string represents gravity. This is kind of how Newton thought of gravity or the force due to gravitation. But it turns out that that specific analogy, the string analogy, and some of his math only works in certain circumstances. So Einstein, hundreds of years later, theorized that maybe gravity is not actually a physical, or rather a direct interaction between two objects like a string would be, but rather the result of an object warping the area around it. So what you're looking at right here is what Einstein has theorized in general relativity, which is now the most commonly accepted theory of gravitation and has a lot of evidence and support for it. So before I continue, I just want to check and see if there have been any questions so far.
Sure. There was one that I tried to answer, but somebody asked, what is this software and is it general public use? Which I said I thought it was.
Yes. So this software is called NASA Eyes, and you can download it for free on the internet if you go to I don't remember the exact URL, but it's NASA Eyes. It's through NASA's website.
I think it's eyes.nasa.gov.
Yeah, I have it on the closing slide, so we should find it at the end. It's just hidden in the back of my computer right now. Oh, good. Our friend said thank you for that answer. So.
Okay, perfect.
Another question. Oh, sorry.
No, go ahead.
So Regina is asking how the sun influences the tide, saying that she was not aware of it.
Yeah, so it's the same way that the moon influences the tide. So its gravitational pull causes the oceans to kind of, swell, or I don't know what the opposite would be, like
Shrink?
Retract, yeah.
Yeah.
And so the sun also has this effect. It's just that the sun is so much farther away than the moon is. So the sun is 93 million miles away from the Earth. So its effects on the oceans on the surface of the Earth is not quite as strong as the moon's effect being so close to the Earth. So depending on how everything is lined up, so like if the moon and the sun and the Earth are all lined up in a straight line, the force of their combined gravitation will cause certain things to happen with the tides. If it's at a 90-degree angle, I actually think that that might be when it's optimized. The tides get really tricky. But when the moon is like at a 90-degree angle between the Earth and the sun, then you have a certain kind of tide. There's like all these really cool names. There's like neap tides,
Spring tides.
Yeah, all kinds of stuff. And the sun does add a little bit into that. It's just not as strong as the moon. So
that's cool.
Yeah.
I don't think I really knew how the sun affected the tide, so I've learned something new today as well.
Awesome.
So we actually had two different groups. Emma first asked this question, and then Ms. Reddy's Rock Stars. So I think we have a school group out there today. They want to know what is the biggest planet, and then Ms. Reddy's Rock Stars also follow up with also the biggest star. So biggest planet and biggest star.
Great questions. So the biggest planet in our solar system is Jupiter. There are bigger planets out there in other solar systems, but for us, it's Jupiter. If you could open it up like a cookie jar, fill it with Earths, you could fill it with over 1,300 Earths. So it is a lot bigger in size, but also mass. So it's made up of more stuff, a lot more stuff than the Earth is. And therefore, it has a much stronger force of gravity because of that. And so it's able to hang on to quite a few moons. You can see some of them here, but Jupiter in total has, I believe, 79 last count, but that does go up every so often. We're always finding new moons. And then as far as the largest star goes, the largest known star, I believe, is named UY Scuti. And I don't know how many suns could fit in it. Talia, do you remember off the top of your head?
It's something absurd, like 1 billion suns can fit inside of it.
Yeah, it's incredibly massive. Like if you were to plop it where the sun is in our solar system, it would swallow up the orbit of Saturn. Like that's how big it is in diameter. Might even swallow up Uranus. I can't recall exactly for now, but it would take up most of the solar system, which is
There's a
wild.
really cool video out there. I think it's a NASA produced, so you can probably find it on the nasa.gov website, but of like the sizes of stars and like scale of the stars. It's really cool.
It kind of goes down the line and shows like what it is compared to the previous one.
Yeah, and then you get to that final one and just how much bigger and how minuscule our sun really is. So I think one more question before we move on, Katie.
Sure.
Riley is asking, is Isaac Newton wrong, or is part of his theory right?
That's a really good question. So Isaac Newton was not wrong. He contributed quite a bit to physics. He just didn't have the whole story, I guess is a good way to put it. So a lot of his math and a lot of his laws, Newton's laws of motion, apply and work for everything in our daily lives. It's just that once you get into really weird situations, like you're talking about objects that have insane amounts of gravity, like a black hole, for example, or if you have something moving really fast, like near the speed of light, that's kind of where his equations and his theories start to break down a bit. And so that's where Einstein's come in, and they encompass a lot of what Newton theorized and a lot of his equations and laws. It encompasses all that. It just includes a little bit more. So he wasn't wrong. He just didn't have the whole story.
It's really cool how like one scientist's work just sort of feeds off the next, and the fact that here in 2021, 400 or almost 400 years after some of those earliest astronomers, like we're still learning new things. And it's even in my time of studying space, the amount of information that we have learned is just great.
Absolutely. Yeah, that's a great way to put it. And even Einstein's theory of gravity, there are still some things that mathematicians are working on and physicists are working on because, it still doesn't necessarily have the entire story, but it works for every scenario so far, almost every scenario so far, including day-to-day motions of objects and orbits and things like that, and these really weird extreme situations as well. All right, so let's go back to Einstein's theory of gravity or general relativity. So he said that objects with mass are actually warping the area around them, causing the effect of a force of gravity. So in this picture right now, you can kind of ignore the cork star down there. It was really hard to find a free picture of a gravity well. So this is the best I could find. But if you want, you can imagine the cork star kind of like the moon and moving in orbit around the Earth. But you can see that the Earth is actually causing a dip in the area around it, which is called the fabric of space-time. So another theory that space and time are connected and they are related. And we actually see this in those extreme situations that I was talking about. And we're actually going to go into special relativity and time dilation and length contraction and all that cool stuff in another Exploring Space this month. So tune in for that one. Unfortunately, I don't have time to get into it right now, but we will cover it. So if we could switch to that video, if you have it up, Talia, I'm not sure if you've got it up, but just for a second to show. So this is just a YouTube video that we found online that illustrated it quite nicely. So you can see the moon orbiting around the Earth in this case. So the Earth is more massive, so it's causing a more dramatic dip in the area around it, in the space-time around it, while the moon is also causing one. But it's not quite as significant. And so you can kind of see this relationship and this curving of their environments. And so an analogy that I like to use is think of a trampoline and think of putting a baseball in the middle of a trampoline. If you look at it from the side, you're going to see that the baseball, because it's got mass, it's got weight, is causing the trampoline to dip a little bit. Now, if you were to replace the baseball with a bowling ball, that dip is going to get much more significant, right? The bowling ball is more massive, and so it causes a stronger dip. So you can kind of think of it like that. Now you can think of introducing a golf ball into this analogy with a bowling ball in the middle. If you were to just place the golf ball, it's going to roll right toward the center, right? Because it's just going to follow that path all the way down. It's kind of the exact same situation, but with this fabric of space-time that we can't really see with our eyes. We just know that it's there because we feel and experience the effects of it in the form of gravity. Which brings us to how do things orbit other things, right? Because we tend to think of space not having any gravity in it at all, which is not the case. Space has a ton of gravity. Remember at the beginning, we said gravity is infinite. It just, works better in closer distances. And there's a ton of gravity in space. And it's the whole reason that planets form in the first place. It's the whole reason that things can stay together. And it's the whole reason that we've got orbits. So let's dive into this a little bit deeper. So let's think a little bit back to the trampoline analogy and with the golf ball. If you just place the golf ball on the trampoline, it's going to just roll right to the center. But what if you gave the golf ball some speed? If you gave it some momentum and you actually pushed it along the outer perimeter of the trampoline and just let it go, it's going to kind of swirl around and around and around and around and around until eventually, because of friction between the golf ball and the trampoline, it'll slow down, it'll lose some speed. In space, there's no friction. So anything that's orbiting something else is never going to fall toward the center unless there's an outside force acting on it. And in most cases, that's not applicable. So like the Earth is like the golf ball around the sun, which is the bowling ball in the middle of the trampoline. And it's just going around and around and around, and it will never actually fall in toward the center. So now let's talk about the astronauts on board the ISS. The ISS is really close to the Earth. It's only about 250 miles above Earth's surface. So it has to be traveling really, really, really fast in order to not hit or fall back down to the surface of the Earth. Because those astronauts, anything in orbit is in free fall. So if you think about skydiving and falling toward the Earth, that's exactly what's happening in orbits or when things are orbiting. It's just that they've got speed. So let's transition to it's kind of like a thought experiment called Newton's Canon. And so this is actually, this original kind of drawing was in one of Newton's books, and this was an artistic rendition of it after the fact. But he basically said if you had a cannon that was massive enough to stick outside of the atmosphere of the Earth and it shot a cannonball, then what would happen? So let's see what happens when we shoot the cannonball at about, let's do 3,000 meters per second and see what happens. All right, so it didn't get very far. So let's maybe increase the speed a little bit and go up to 5,000 meters per second. All right, so we see that it got a little bit farther. Let's do 6,000 meters per second. All right, got a little bit farther, so you can see the pattern happening here. Let's do 7,500 meters per second. Thank you, Talia. All right, so now it's got quite enough speed, right? It's not actually hitting the surface. It's got enough speed that every time it falls, it's essentially missing the Earth because of the curvature. So this is how orbiting works. Now, if you were to get a speed of even higher, you would have a bigger orbit. So you can get things even farther out into space. And so that's why the ISS has to go so fast, is so that it doesn't end up like those first few flight paths that we see there, right? That would just come falling down. It needs to be going fast enough that it never actually hits the Earth. It always misses because it's going too fast. So that's how orbiting actually works. Same thing for all of the planets and even things that are on a bigger scale. So we've talked a lot about our solar system and things that are in orbit around the Earth, and we talked about the tides a little bit, but we see things orbiting on much bigger scales. So when we look at other stars in the nighttime sky, most of those stars are actually part of binary systems. So stars that are actually orbiting around each other. Now, stars are very massive, and a lot of the times they're massive enough that they're almost equivalent in their mass or gravitational pull. So if you've ever seen like a simulation of a binary star system, they're actually moving around each other instead of one moving around the other because their masses are comparable. We also see extreme gravitational forces around a black hole. So black holes are a result of a really massive star dying, collapsing into a teeny tiny space, and then causing this massive, I guess that's a little bit of a confusing word to say, but this really deep gravity well. So that dip for a black hole is going to be incredibly deep.
I apologize, Katie. I am trying to show the visuals that go with these examples, but
no worries.
I think my program is getting grumpy.
No worries at all. I asked Talia to show all of these crazy visuals. That is probably too much for computers to handle, so that's my fault. Galaxies are also gravitationally attracted to each other. So like our own Milky Way galaxy is orbiting around the Andromeda galaxy, which is also very massive. And so eventually they will collide. We see a lot of that happening all over the universe. And so really understanding gravity and understanding at least the effects of gravity and how it works, at least, is really important for space exploration. Without it, we wouldn't be able to leave the Earth. We wouldn't be able to send spacecraft to other places in the solar system. And it would be imaging, even looking through telescopes at other places in the cosmos, other galaxies, things like that becomes a lot easier once you really kind of understand how gravity works. So to give you some examples of that, we have getting rockets off the surface of the Earth, right? We saw from that Canon simulation that you have to go a certain speed in order to actually escape the Earth. It's called the escape velocity, so that gravity doesn't drag you back down. I believe that's around 26,000 miles per hour. The farther you want something to go, you have to account for these types of interactions. Like when we sent New Horizons to Pluto, that spacecraft had to go incredibly fast to make it there in a reasonable amount of time. But since it was going so fast, it wasn't able to hang out around Pluto. It was never able to actually get into orbit around Pluto. It had to just fly by because it was going too fast. We also use gravity in hunting for exoplanets. So as I said earlier, planets also pull on stars that they orbit. And so when we're looking at the light from other stars in other solar systems, you can actually see little shifts in the light because of planets pulling on their star. It's called the wobble method. And then there's also gravitational lensing, which is something that I find really fascinating. It's when astronomers are looking at an object that is really massive. So say astronomers are looking at a galaxy, and it turns out that there is, another galaxy behind it that's much farther away. The gravitational force of this foreground galaxy can actually be so strong that it bends the light of anything behind it, causing these images to appear. And thus you can actually see behind other, so here's a visual. So we've got that galaxy kind of in the foreground galaxy with 4 quasar images. You don't have to worry about what a quasar is, but just think of it as a star for now. And then you've got this really bright source, the quasar or the star, in the background. And so you've got the light coming up, and because this galaxy is so massive, it's causing the light to bend around it. And so when you're looking with, in this case, the Hubble Space Telescope, it's seeing 4 separate images above and below the galaxy on either side of it. So that is gravitational lensing, and it allows astronomers to see billions of light years away. So it's super helpful, super useful. These are real images of gravitational lensing happening in action. All right, I talked a lot, so maybe we have time for 1 or 2 questions.
Perfect. There are a bunch that have come in. I think this is back when you were talking about the planets and how they stayed in orbit. And someone asked, can planets get hit out of orbit? And if so, do they continue endlessly into space?
Yeah, so when I mentioned like they'll stay that way unless there are any other forces that either interact with it or anything like that, that's true. So like if you have a really big collision, you can send it on a different path, or if it's a really, really, really high intense collision, you can completely knock, an asteroid or, a moon out of its orbit. A lot of the moons around the gas giants are captured moons because they were floating by and got stuck in orbit around the planet. So that can absolutely happen.
Cool. And then maybe one last, I know we're right at 3 o'clock. How many planets are in space and how big is space?
Oh my goodness.
How many planets?
Yeah, so in terms of known planets that we've discovered and confirmed are planets, I believe it is just over 4,000 or 4,100. But that's just in our local part of our galaxy. It's estimated that there are the same number of planets as there are stars in the entire universe. And we know that there are about 300 billion stars in the Milky Way, and that there are around 1 trillion galaxies in our observable universe. So you can do that crazy math and get a very, very high number of how many planets are probably out there.
That's a lot, and so cool to think about just how tiny we are in the grand scheme of the ultimate universe. So that was a lot of information from Katie and Talia's amazing flying behind the scenes. So I want to thank both of you for sharing that. Well, it's not your fault your program crashed. You did your best, but thank you both for sharing all of this with us today.
Thanks, everyone.
Perfect. And then I want to thank all of you out there that chose to spend some of your Tuesday afternoon with us learning more about gravity in the universe, which was a really cool topic. If this is something that you were really intrigued by, want to know more of what we're doing, you can always check out our website, MOS at Home, for all of our live stream, and as well as asynchronous content that is all over our website for you guys to watch at your leisure. If you are able to do so, we would love you to think about supporting the museum by going to that address below. And then lastly, for the folks that were asking, NASA EYES is the program, and it's eyes.nasa.gov, just I think what Talia had said. So I hope that you guys enjoyed it. You learned some new facts. I certainly did as well, and we'll see you next time. Thanks, everybody.